Hey guys, so this is Gully, and we are going to go over the Redox Titration pre-lab. So get out your lab notebook, and we're going to have to write down some stuff and everything to be able to save time in class. So first of all, the title of this lab is Redox Titration Lab. You'll end up putting the date whenever you get into class to do the lab. So take a second here and go ahead and copy down the purpose and the materials. Our purpose when we do this redox titration lab is to determine the concentration and mass percent. So we're pulling back a little bit of stoichiometry with concentration. Remember, concentration and molarity is the same thing. And mass percent, remember that that's part over whole when we're looking at masses of the household hydrogen peroxide. So that's H2O2 using the redox titration lab technique. So what we're going to be doing is using the following materials. We'll need a burette to be able to measure volume, a beaker. That beaker will hold our stuff, the hydrogen peroxide. We'll add some sulfuric acid to that because this reaction can only occur if it's in acidic conditions. You might have watched a video earlier on how to balance half reactions when we're working with acidic conditions and things like that. So you might have to do that in your pre-lab. The potassium permanganate is what we're going to be using in our burette. And then the hydrogen peroxide is what we're going to be analyzing, and that will be in our beaker. So go ahead and write down those purpose and materials. You can stop this video if you need to. There's a couple of notes that we want to go through before you guys just dive right in. So a lot of terms, you guys say that vocabulary is a big thing we need to know. So make sure that you guys just take these notes down in your lab notebook somewhere. So first of all is the titration setup. So the picture on the left here, you see that you have a long skinny tube, and that's known as the burette. What you do is you put your titrant in the burette. So the titrant is the solution that is standardized. Now, what that word standardized means is that we know the exact molarity of that thing. We are going to have to use that information to help us with calculations. Then we have the analyte. The analyte is what you see at the bottom. Right now it's a picture of an Erlenmeyer flask down at the bottom, but we're just going to use a beaker for our analyte. So it is the solution that is unknown. Because our hydrogen peroxide is going to be our unknown thing, that is going to be our analyte. And because our potassium permanganate is going to be the thing that is standardized, meaning we know its exact molarity, that will go in our burette as our titrant. Now, later on in the year, we're going to do another titration, which is known as an acid-base titration. So what I think is really important for us to kind of go ahead and get an understanding for is what is the difference between a redox titration versus an acid-base titration. Well, I'm going to go ahead and give you the bad news. Both include stoichiometry, which is a lot of your nemesis, but you got to embrace it, you got to love it, you got to apply it to all of these new things. So when we do a redox titration, it's just stoichiometry. We get into moles, we do a mole to mole ratio from a balanced reaction, and then we answer our question of whatever we're trying to find. For acid-base titration, same deal. We're going to use information given to us to get into moles, do mole to mole ratios based upon the balanced reactions, and then answer the final question. So a lot of students do get confused on what is the difference between an acid-base titration and a redox titration if they're both just an application of stoichiometry. Acid-base titrations, and we're going to do this one later in the year when we cover the acid-base unit in January. You get a color change in your analyte. So your analyte, remember, is the solution that is unknown. It is the solution that will be in the either beaker or Erlenmeyer flask at the bottom of your setup. The reason why you get a color change in acid-base titrations is because you have to use a different chemical called an indicator. The indicator allows a color change to occur, and that's when you know to stop your titration and collect your data. Now, the reason why you have to introduce an indicator is because when we have acid-base titrations, we're transferring protons, which is H positives. All that means, the H plus means a hydrogen has lost an electron, so now it's just a proton remaining. And so when we're working with acid-base stuff, we're transferring stuff, but the things we're transferring are protons. When we do a redox titration, however, which is what we've been working on with our reactions, we do get a color change, and we're going to talk about that color change in a minute, but it's due to the changing of the oxidation states. The oxidation states are changing because we're transferring electrons. So that's where the reduction and the oxidation occurs. That's electrons we're transferring. So what is the main difference of an acid-base titration versus a redox titration? They both contain stoichiometry or apply stoichiometry. They both get a color change, but your color change in the acid-base titration is due to an indicator transferring protons, whereas the color change in a redox titration doesn't need an indicator, and that's due to the changing of oxidation states because you're transferring electrons. So getting into that color change, all of these different cations, these things that are positively charged, naturally have certain colors. And so you might want to write this down in your lab notebooks, just so as we're doing stuff throughout the year, you can kind of see the different oxidation states and why we get different color changes. Now, we have seen the copper 2 plus before. When we did the hydrate lab and the copper 2 ions in the hydrate were embedded in there, that crystal was a pretty blue. The blue there is because the copper 2 ions are giving that certain color. We are going to be working with potassium permanganate, and permanganate in potassium permanganate is a +7 oxidation state. And so what we will see for our color there is a violet. Now we will be transitioning, we will be creating a reaction, and we'll see that the hydrogen peroxide turns a really cool color due to those oxidation states changing. And that's something I kind of don't want to give away. Maybe you saw it in one of the previous videos for the lab, but I kind of want you to see that in the class for yourself. So we are going to see a color change. What that color change is depends on what we're working with. Now, I want you guys to take a minute and write down these pre-lab questions, especially write down this reaction. This reaction is going to be really important for you because remember, we're going to need it for the stoichiometry. And what you'll see here, notice that how I said we're going to be working with potassium permanganate, but you don't see potassium anywhere in that reaction. That's because the potassium is a spectator ion. The reaction that you see here is the net ionic equation. And so that's why you don't see potassium, but it's not going to hinder. We have our balanced reaction. We have our multiple ratios there to be able to apply the stoichiometry, so we're good there. So I want you guys to answer these pre-lab questions before you come to class. We're going to go over these questions first thing before we start our lab. And so the first question is determine the oxidation states of each species in the reaction. So what that means is I want the oxidation state of Mn, of oxygen, of hydrogen, of oxygen, of the H plus on the reactant side, and then on the product side, oxidation state of oxygen, hydrogen, oxygen, and Mn2 plus. So I want you to find each oxidation state. Based upon those oxidation states, you can answer number 2 and number 3. Identify the species reduced, justify your answer, simulate that like the redox practice that we talked about and the single displacement reaction practice that we've talked about. How do we justify that something's reduced versus identify the species who's oxidized? How do we justify for that? For number 4 and 5, these are going to be a little bit tougher half reactions for you guys to do. So what you need to use is the balancing redox and acidic conditions notes that you guys watched previously before you dived into this video. So I want you guys to take a stab at it, see how you go. Remember, we just pick apart the pieces that are reduced, pick apart the pieces that are oxidized, and then you'll have to do some more steps after that. But that's all that you guys need to do for your pre-lab. Make sure you wear closed-toed shoes and have all of this stuff ready by the time you come to class on Wednesday.